Welcome to our quantum deep dive. Today, we're going right to the edge of physics. We're going to meet one of the most extreme, most mysterious particles out there, and this entire explainer is based on some fascinating work by Jörg O. Schnippert.
All right, let's dive right in and meet the star of today's show, the anti-top quark. Now, the best way to think about it, it's like a heavyweight ghost. It's the most massive and, one of the most elusive bits of antimatter we've ever run into.
So, what is this thing really? Well, think of it like this. For every single particle of matter, physicists figured there has to be a matching antiparticle, kind of like a perfect mirror image, but with an opposite charge. And that's exactly what the anti-top quark is. It's the mirror image of the heaviest elementary particle we've ever found, the top quark.
And listen, when we say heavyweight, we are not kidding. Just forget the technical numbers for a second and wrap your head around this. A single, fundamental anti-top quark is heavier than a whole atom of gold. I mean, just think about that. A gold atom is this big, packed cluster of hundreds of smaller particles, and yet this one lone quark outweighs the whole thing. It's just unbelievably dense.
But this is where the ghost part comes in. It is so unstable. It exists for a fraction of a second, so tiny it's almost impossible to even imagine. It's gone before it has any chance at all to bond with other quarks and, form bigger particles. And that's what makes it totally unique. It's the only quark that scientists can actually study in its pure, free state. It's like a direct window into the fundamental laws of nature.
And right here, you can see that perfect mirror symmetry in action. Take a look. The mass? Exactly the same. Its spin? Its intrinsic angular momentum, also identical. But then you look at the electric charge, and it's perfectly opposite. One's positive, the other's negative. It's just this beautiful, precise symmetry you find in the subatomic world.
Now, a particle this extreme, you don't just stumble upon it by accident. Nope. It was first discovered as like a ghost in the equations of physics. It was predicted decades before we had any technology that could possibly find it. The theory was just sitting there, waiting for us to build a machine powerful enough to bring it into reality.
And the hunt for this thing was, it was a scientific epic that spanned decades. It all started way back in 1928 with Paul Dirac's math, which predicted antimatter. Then, in the 60s, the quark model came along and pretty much demanded that a sixth top quark had to exist to make everything symmetrical. The hunt really heated up in 1977 when they found its partner, the bottom quark. And finally, boom, 1995. At Fermilab, two massive international teams finally cornered their prize, finding top and anti-top quark pairs and proving all those theories were right on the money.
And you've got to understand, this discovery wasn't just about ticking another particle off a list. No way. This was the final, missing piece of the entire puzzle. Finding that top/anti-top pair. It was the capstone. It completed the standard model of particle physics. Without it, our whole fundamental theory of matter would have had this huge gaping hole.
Okay, so we know what it is, we know how it was predicted, but how in the world do you actually make something so massive and so short-lived? I mean, you can't just go out and find these things. You literally have to forge them.
And to forge antimatter, you need the most powerful machine on the planet, the Large Hadron Collider. It's kind of like a four-step recipe for creation. First, you accelerate protons to just shy of the speed of light. Second, you smash them together head-on, creating a fireball of pure energy. Third, inside that fireball, Einstein's E=mc² kicks in, and that pure energy converts into mass, popping out particle-antiparticle pairs. And finally, since the anti-top quark vanishes in an instant, scientists have to be clever and detect the signature children it leaves behind.
But this whole creation process, it's not random. The main way it happens is through something called gluon-gluon fusion. Now, gluons are exactly what they sound like. They're the particles that literally glue protons together. So in these incredibly violent collisions at the LHC, every now and then, two of those gluons from opposing protons will just smash right into each other. And all that energy forges a brand new top/anti-top pair. It's a direct display of the just awesome power of the strong nuclear force.
All right, so we can make this fleeting ghost particle in a lab. Cool. But why does it matter? Why go to all this trouble? Well, because understanding this little particle could hold the key to one of the biggest mysteries of all time, our own existence. We're about to go from the super small to the biggest question there is. And that question is,
Why are we here? No, seriously, why does our universe, this thing made of matter, even exist? All of our best theories tell us the Big Bang should have created equal amounts of matter and antimatter, and if that's what happened, they would have just instantly annihilated each other. Poof, gone, leaving behind nothing but a bland sea of light. So why is there something here instead of nothing?
This huge cosmic puzzle has a name. It's called baryogenesis. The idea is that something somehow must have tipped the scales just slightly in favor of matter. We're talking by about 1 part in a billion. And because of its crazy mass and really unique properties, the anti-top quark is now a prime suspect in this cosmic whodunit. Physicists are wondering, did it behave just a little bit differently from its matter twin in the heat of the early universe?
So to solve this mystery, the physicist Andrei Sakharov said 3 conditions had to be met. Now for our story, the really crucial one is the second, a violation of symmetry. What does that mean in plain English? It means that matter and its antimatter mirror image can't be perfectly identical in how they act. There has to be a tiny, tiny difference. So right now, scientists at the LHC are meticulously studying top and anti-top quarks, hunting for that exact subtle difference in how they're made or how they fall apart. If they find even a slight imbalance, that could be the smoking gun that explains why we're all here.
So why is the anti-top quark the main suspect here? Well, it all comes back to its weight. It's just so incredibly heavy. That huge mass means it has the strongest connection of any particle we know to the Higgs field. That's the field that gives everything mass in the first place. This makes it the perfect tool, like a hypersensitive antenna, for sniffing out new, undiscovered particles or forces that could be the real culprit behind that matter-antimatter imbalance.
Okay, I know this all might sound pretty theoretical, right? A cosmic mystery from 13.8 billion years ago. But what's amazing is that the intense study of the anti-top quark is already shaping the future of our technology, specifically in the revolutionary world of quantum computing.
Here's the thing. Trying to simulate the bizarre quantum world of an anti-top quark's life and death is it's impossibly complex for our best supercomputers. They have to cheat, basically, using approximations and shortcuts, but quantum computers, they're a completely different beast. They're built on the very same weird principles of quantum mechanics, things like superposition and entanglement, so they can simulate these interactions directly, which promises a level of accuracy we've just never had before.
And this creates this really powerful synergy. See, the anti-top quark isn't just something for quantum computers to study, it's a challenge that's actually driving their development. Its insane complexity is inspiring brand new quantum algorithms. For instance, some are designed to calculate the immense energies involved, others to simulate the strong force that holds it all together, and some even use AI to hunt for rare patterns in all the data. Basically, if you can build a quantum computer that can accurately model the anti-top quark, you know you've built one heck of a powerful machine.
Which kind of leaves us with this one big provocative thought. From explaining why our matter-filled universe even exists to driving the next huge revolution in computing, could it be that this one fleeting ghost particle is actually the key to, well, everything?
It really is a key that might one day unlock some of the deepest secrets of our reality. We really hope you enjoyed this deep dive with us. It was adapted from an essay by Jörg Oe Schnoppa.
For more information, and if you want to read that original essay for yourself, you can head over to schneppat.de. Thanks for joining us, and goodbye for now.
Schneppat.de is a private project by Jörg Oe Schneppat dedicated to promoting quantum technology. Its mission is to present knowledge in a way that is clear, precise, and transparent for those just starting out, as well as for experts who wish to deepen their expertise. He firmly believes that education and access to well-structured information are the keys to unlocking the full potential of this future technology. If his work helps you realize your own visions and actively and consciously shape quantum technology, then the goal of his project has been achieved.